Welcome back, everyone. If you're a focused learner gearing up for that CCNA 200-301 exam, well, you're in the exact right place. Today's explainer is your absolute ultimate guide to mastering the raw technical blueprint of network topology architectures. We're going to break down the operational functions, the specific design goals, the whole shebang of the most critical network architectures you actually need to know. I'm incredibly pumped to share this with you, so grab your notes, get comfortable, and let's jump right in. Okay, so let's dive into the overarching problem here. Just think about the modern digital landscape for a second. How on earth do networks achieve this massive scale, handling thousands of devices and literally petabytes of data, without just completely collapsing under their own weight? Well, the answer comes down to deliberate, highly engineered network design. We absolutely need networks that offer incredible scalability and, of course, rock-solid predictability. So here's our roadmap for today. First, we'll look at the three-tier hierarchical model, then the two-tier collapsed core. After that, we'll hit the spine leaf revolution. And finally, we'll wrap up with mastering network architectures. Part 1. The three-tier hierarchical model, the classic baseline. Now, to really get this model, you've got to understand its core purpose. We're essentially constructing a three-layered networking cake here. This design intentionally separates critical network functions into three distinct physical layers of hardware. Why? Well, to hit three highly specific engineering goals: scalability, modularity, and predictability. You see, by dedicating specific hardware to very specific tasks, the whole network becomes highly organized and incredibly reliable. Let's build this network from the bottom up. Right at the base, we have the access layer. This is the very first place a device connects. It's the entry point into the network fabric for endpoints like your PCs, your IP phones, and those wireless access points. From an engineering standpoint, this layer primarily handles Layer 2 switching. It gives you that initial device connectivity, it defines your broadcast domains, your VLANs, and it acts as your first line of defense, enforcing edge security protocols like port security and 802.1. Moving up one level, we hit the distribution layer. This layer aggregates all of those access layer switches below it and connects them straight up to the core. So the absolute crucial takeaway here is that the distribution layer acts as the brain of the network. This is where policy is strictly enforced. It serves as that critical boundary between Layer 2 VLANs and Layer 3 routing. All of your complex inter-VLAN routing, your quality of service classification, and your security filtering using access control lists, they all live right here. Plus, it uses protocols like HSRP and VRRP to completely eliminate any single point of failure by connecting to multiple core switches. Finally, sitting at the very top is the core layer. This is the high-speed backbone of the network, and honestly, its only job is pure speed. It's designed to switch packets as insanely fast as possible, handling massive north-south traffic movement, which just means traffic moving up to the internet or down to the users. To pull this off, the core relies on extremely powerful, non-blocking hardware known as ASICs. And let me tell you, redundancy at this level isn't just a good idea, it's absolutely mandatory. But here is the strict engineering law you absolutely must remember for the exam. At the core layer, there is zero policy enforcement. That means no ACLs, no complex routing decisions, and zero security inspection. Why? Well, because doing those things takes processing time. You absolutely cannot introduce latency at the core. It is about pure, unadulterated speed, and that's it. Part 2. The two-tier collapsed core, the compromise. So let me pose a very practical question to you. What if your deployment just isn't large enough to justify the sheer cost and the complexity of a full, robust three-tier design? I mean, medium-sized enterprise campuses or branch offices often face really tight budgets and physical space limitations, right? To solve this exact problem, we actually physically merge the top two tiers together. Functionally, it operates a whole lot like the three-tier model, but the dedicated function of the core layer is collapsed directly into the hardware of the distribution layer. By doing this, organizations save significantly on physical space, power consumption, and capital expenditure, all while maintaining that vital modular access connectivity right at the bottom. However, that CapEx savings, it comes with a pretty heavy engineering cost that you definitely need to be aware of. Because we've merged those layers, these collapsed devices have to be incredibly powerful. They have to simultaneously handle complex policy enforcement, like your routing, your ACLs, and your VLAN aggregation, and they still have to perform high-speed backbone switching at the exact same time. The hardware literally has to do double duty. Part 3. The spine leaf revolution, the paradigm shift. Now, this brings us to a brilliant illustration of exactly why the old three-tier model is kind of failing in today's modern data centers. It's all about the traffic shift. Traditional three-tier networks were heavily optimized for north-south traffic, users connecting up to servers. But modern data centers, they're driven by application virtualization, storage, and clustering. This means the vast majority of traffic is now east-west, which is server-to-server traffic. If you try to push massive east-west traffic through a traditional three-tier design, you're going to introduce some highly unpredictable latency. The spine leaf architecture was invented to solve this exact problem. Let's break down this new physical layout. In a spine leaf architecture, we actually only have two layers. First up are the leaves, which essentially act like the access layer. These leaf switches are what your physical servers and storage arrays actually plug into, and conceptually, they perform those L2/L3 boundary functions. Then we have the spines. These completely replace the core. They act as the ultimate high-speed backplane, but here's the kicker. Instead of a hierarchical tree, every single leaf switch connects up to every single spine switch in the entire fabric. This layout builds a completely deterministic, rock-solid predictable network path, using some very strict engineering rules. Rule number 1, spine switches never connect to other spines. And rule number 2, leaf switches never connect directly to other leaves. Honestly, if you can just understand those strict separation rules, you've practically mastered the raw concept of spine leaf wiring. Because of those strict rules, we get this massive exam-critical number, 2. In a spine leaf fabric, every single endpoint on any leaf is exactly 2 hops away from any other endpoint on any other leaf. Think about it. Server to leaf, leaf to spine to destination leaf. Boom, 2 hops. This utterly destroys that traditional unpredictable latency. Furthermore, the fabric utilizes equal-cost multipath, or ECMP, routing to load balance traffic across all available spines simultaneously. This creates a non-blocking linear scalability model. Want more server density? Just add more leaves. Want more fabric bandwidth? Add more spines. It's a real game changer. Part 4. Mastering Network Architectures. The final blueprint. Okay, here is your ultimate blueprint to map all this out. Notice how the 3-tier and 2-tier models are really best suited for enterprise campuses focusing on that north-south traffic. Conversely, spine leaf is the undisputed king of the modern data center, focusing entirely on east-west traffic. And just a quick reminder, to achieve that massive linear scalability we just talked about, spine leaf typically runs advanced layer 3 routing protocols, like BGP or ISIS, to handle all that ECMP routing. I want to leave you with this provocative thought as we wrap up this explainer today. Given that modern applications and virtualization are causing east-west traffic to grow at just an exponential rate, even outside of traditional data centers, do you think the classic 3-tier hierarchical model will eventually become entirely obsolete? It's a pretty fascinating question to ponder as you continue your journey into modern network design. Thank you so much for joining me. Keep studying hard, and I'll catch you next time.